We're continuing on with Unit 6 Lab Math Part 2, which will cover dilutions. Many of the laboratory procedures you will be performing involve the use of dilutions. It's very important that you have a complete understanding of the concepts of dilutions, since they are a very handy tool used throughout all areas of the clinical laboratory: microbiology, blood bank, serology. These dilutions have to be considered as they make a quantitative difference in what is going on. Dilution, by definition, is the action of making a liquid weaker by mixing it in something else. So, for example, making orange juice from frozen concentrate. I don't know if they still make this anymore, but the concentrate would come in a can, and it was very, very concentrated. It'd just make your lips pucker if you tasted a little bit of it. So what you did was you dumped the can of concentrate into your pitcher, and then you would add 3 cans of water and mix it very well. Dilutions are expressed as the volume of the solution being diluted per the total final volume of the dilution. So for example, in the orange juice example, the dilution would be expressed as 1 over 4. We had 1 can of the concentrated orange juice. We added 3 cans of the diluent, which is the water, and mixed it up. So the total volume when I added the 1 can plus the 3 cans is 4. Of the 4 parts, 1 is orange juice. So what this is written as is 1 in 4. Another example is if you dilute 1 milliliter of serum with 9 mLs of saline. The dilution would be written 1 over 10, or we pronounce it 1 in 10, because again, we have 1 part plus 9 parts. So the number on the bottom is the total volume. Of that volume, 1 part is serum. So again, that's where we get the number 1 in 10. Another example is we have 1 part of concentrated acid, and we dilute with 100 parts of water. Now, remember your laboratory safety, A and W. Always add acid to water. If you add water to acid, you're going to end up with an explosion. So I teach my students A and W, acid to water. So the total solution volume is 101, because we have that 1 part of acid, but we have 100 parts of water. So how we say this type of dilution is 1 in 101. One thing I want you to notice is that dilutions do not have units. We don't use cans, we don't use milliliters or parts, but they are expressed as one number to another number. So again, our example, 1 over 10 is 1 part in a total of 10 parts. Dilutions are always expressed with the original substance diluted as 1. If more than 1 part of the original substance is initially used, for example, 2, it's necessary to convert the original substance part to 1 when the dilution is expressed. This gets a little confusing. The next slide will provide so I want you to spend some time with this example. So we have 2 parts of dye, and we're diluting it with 8 parts of diluent, the term often used for the diluting solution. So the total solution volume is 10. And so how we get that number, we have 2 parts of the dye and 8 parts of the diluent. So those together is 10. The dilution is initially expressed as 2 over 10, but again, that number on top must be 1. So to get the original volume to 1, use a ratio proportion equation, remembering that dilutions are stated in terms of 1 to something. This is where your basic algebra comes into play. So we solve for x. So we know 3 parts of this equation. We know we have 2 parts of the dye. We know we have a total volume of 10. And we know that we need to express the top number as 1. So what is x? So we break down the equation. 2x equals 1 times 10. So x, you move the 2 over to divide the 10 by 2, is 5. So dilution is expressed in 1 to 5. So again, we had 2 parts and 8 parts, which is 2 over 10, but the number on top must be 1. So you need to break down the numbers to where we have that 1 on top. The dilution does not always end up in whole numbers. And this is unusual because we like nice rounded numbers. But here's an example of a time when it wouldn't be. So again, we're going to have 2 parts of whole blood, and we're going to dilute that with 5 parts of saline. So the total solution volume is 2 plus 5, 7. So that's going to be your bottom number. The number on top is 2 because we had 2 parts of the whole blood. Oh, and we added that to 5 parts of saline, so we have that number on the bottom, which is 7. Or correctly is, again, we must get that number to 1. We have 1 and 3.5. So again, you set up your equation. We know 3 parts. We know 2 parts is blood. We know the total volume of the diluent plus the blood is 7. We know that we have to express that top number as 1, so we're solving for x. So we have 2x equals 7. You divide 7 by 2, and we end up with 3.5. And you thought you'd never have to use algebra again. Another important concept is the dilution factor. And this is used to correct for having used a diluted sample in a lab test rather than the undiluted sample. And this will become even more important when we talk about serial dilution. So this is the formula for dilution factor. It's the volume of substance 1 plus the volume of the diluent divided by the volume of substance 1. So let's say, for example, that we had 0.5 of the substance we're going to dilute plus 4.5 of the diluent. So you put that on top of the equation and add it together, and then you divide by the volume of substance 1, which is 0.5. And if we do the math, then that will break down to 10. So the dilution factor will be 10. This number would then be used to multiply dilutions of all subsequent tubes. And I'm going to show you some examples of this. So again, this is used in serial dilutions where every volume of diluent is the same. So we have 4.5 in every single tube. We add 0.5 of undiluted substance to the first tube. We mix it very well, transfer 0.5, and so on. So the first tube would have a dilution of 10. The second tube, again, our dilution factor is 10, so we'd multiply 10 times 10. So the dilution of the second tube would be 100. Then again, we transfer 0.5 to 4.5, mix it really well. That then again dilutes it by a power of 10. So 10 times 100 is 1,000. Another application of a dilution is sometimes when analyzing a blood sample, the results are above the linearity or accuracy of the machine. For example, there are reagents added to react with the substance we're testing for. If the substance we're testing for is a large amount, then the reagent is used up before it can convert everything. So we end up with a falsely decreased result. When this happens, and your procedure manual will tell you, and a lot of the modern machines will let you know when the result exceeds the linearity of the machine. In that case, you have to dilute out the sample, retest it, then result is multiplied by that dilution factor. So here's an example. The technician performs an analysis of the patient's serum for a glucose, which is also known as blood sugar. The patient's serum glucose was too high to read on the glucose instrument. So what was done, and sometimes if you're lucky enough to work in a lab, the machine will automatically do this dilution for you. But if not, you have to go by your standard operating procedure to do a dilution of the sample. So in this case, we're going to dilute the patient's serum 1 to 2 and run on the analyzer again. So we ran it, and the result was 210 grams per deciliter. Now, that is not the result, because remember, we diluted the sample out. So you have to multiply that result by the dilution factor, which is 2. So in this case, the corrected result is 420 grams per deciliter. Another example is that sometimes it's necessary to make a dilution of an existing solution to make it weaker. For example, we have 100 milligrams per deciliter solution of substrate that's needed for a laboratory procedure. All that is available is a 500 milligram per deciliter solution of substrate. So a dilution of this stronger solution of substrate is needed to get the concentration of 100 milligrams per deciliter. So another application of dilutions is making a weaker solution from a stronger one, and you need to memorize the formula. So V1 stands for volume 1, and we need, if you look below, we need 100 mLs. C1 is the concentration. We want the concentration of this 100 mLs to be 100 milligrams per deciliter. V2 is the volume. How much of the 500 milligrams per deciliter do we need to make 100 mLs of the 100 milligrams? So you set up the formula. The only unknown is the volume needed of the 500 milligram per deciliter concentrate. So if you perform the math, V2, we need 20 mLs of the 500 milligram per deciliter solution, and then we add enough water to bring that up to 100 mLs, which would be 80 mLs of water. So we've just learned about making dilutions singly, as shown in the previous examples. Or we can make dilutions in a series, in which case the original dilution is diluted out further. A general rule for calculating the dilutions of solutions obtained by diluting in a series is to multiply the original dilution by subsequent dilutions. And serial dilutions are very commonly performed in serology and microbiology. So you will see this figure in serology texts, in information you find on the internet. This is an example of a serial dilution. So we have our stock, our full strength stock. In our world, this is usually a patient sample. Every tube will have 9 mLs of diluent in it. So you start off with all the tubes having the 9 mLs. What we do then is we take 1 ml from that stock concentrate and we put it into the first tube. We mix it thoroughly, usually by raising the volume of the fluid 3 times in our pipette. Then we take 1 ml of that diluted sample and transfer it to the next tube, and so on, however far out you want to go. So in the first tube, we have 1 part of the patient's serum plus 9 parts of the diluent. So we have 1 in 10. There's 1 part of patient sample in a total of 10. So the dilution factor, if we were going to calculate that out, would be 10. Then when we transfer to the next tube, it's the same dilution factor, it's 10. So you would then multiply that number by 10. So 10 times 10 is 100. So now in that second tube, we have 1 part of patient sample in a total of 100 parts of diluent, and so on. So I'll explain it one more time because it is so important that you get this concept down. When we add 1 ml of a concentrate to 9 mLs of diluent, the total volume is 10. The parts in that volume that are the stock solution is 1. So that's 1 in 10. Then we take 1 ml of that 1 to 10 solution and we put it in 9 mLs of diluent in that next tube. Then the second tube also has a dilution of 1 to 10. But remember, what we put in that tube was already diluted. So we take a 1 to 10 and we further dilute it 1 to 10. You multiply those numbers and you get 1 to 100. If we continue this serial dilution into the third tube, we then will mix. We will have 1 ml of a 1 to 100 solution, and we add that to 9 mLs of diluent. So we have further diluted that by 10. So that tube would have 1 to 10 times 1 to 10 times 1 to 10. This tube would have 1 part of our patient sample or stock solution. So let's do a little bit of practice. What is the dilution factor when 0.2 milliliters is added to 3.8 milliliters of diluent? So let's set up the dilution factor problem. We have 0.2 of the concentrated plus 3.8 of the diluent for a total volume of 4.0. Then you take that final volume and you divide it by the aliquot. So we end up with a 1 to 20 or a dilution factor, which is the 20. This would be explained as 1 part of concentrated solution and 20 parts total. The reason this type of dilution is done is to reduce the volume. We could add 1 part of concentrate to 19 parts of diluent, but that final volume would be 20. And if we're talking about milliliters, that would be a pretty darn big tube, versus having a total volume of 4 would require a much smaller tube, and it's just a lot easier to deal with. I know you're going to get very tired of me saying this, but it's so important that you remember that serial dilutions are always made by taking a set quantity of the initial dilution and adding it successively to tubes with the same volume of diluent. So each successive dilution would be multiplied by the dilution factor. So in the previous example, we set up our tubes and we add 3.8 mLs of diluent to each tube. We would then transfer 0.2 mLs of the initial diluted sample into the next tube. Mix real well, transfer 0.2, mix real well, and so on. If you had 4 tubes, what would be the final dilution? So here we go. We have the tube, we have the aliquot, we have the diluent. Notice that every tube has 4.0 mLs total volume. So we do the math. We find out that the dilution is 1 to 20, and remember the dilution factor is 20. So what you do is you multiply each tube result by 20. So the next tube is 20 times 20 is 400. The next tube is 20 times 400, which is 8,000. So every tube is multiplied by 20. Or if you simply wanted to know the dilution of the final tube, you could just multiply them together. When we're performing serial dilutions in the clinical laboratory, you must know the dilution of each tube. So what we do is, based on the standard operating procedure manual, we create a procedure, and in that procedure we have a chart. And so the chart indicates what volume of the diluted substance will go into each tube, along with what volume is in each tube of the diluent, and then we calculate the dilution factor and we fill in the chart on the bottom. So we know that tube 1 is 1 to 2, tube 2 is 1 to 4, and so on. So again, whoever created the chart, you have to know that dilution factor so that you multiply each successive tube by it, and you can easily determine the concentration. And I want to emphasize again that titers are reported as the reciprocal of the last tube giving a positive reaction. If tube 2 was the endpoint, the dilution is 1 to 800. The titer is reported out as 800 over 1. Break that down as 800. So again, the dilution is 1 to 800, but the titer is 800. In summary, you are very fortunate because math is not used much in the clinical laboratory, as almost all of our reagents come pre-diluted to concentrations needed for our analyzers, and formulas are built into the system to calculate results as needed. The most frequently employed math skill is preparing dilutions. Some analyzers will recognize an out-of-range result and automatically perform the dilution and the calculation to give you the correct result. Most analyzers will not, and you must pay careful attention to determine if a result is out of range of the analyzer. And once the diluted sample is tested, the results must be multiplied by the dilution factor. Other areas of the laboratory may require dilutions of patient samples or reagents, for example, serology and microbiology, to name a few. The most commonly performed dilution series is the serial dilution, which is reported out as a titer. A measles titer is frequently performed on pregnant women to determine their risk. So her serum is diluted out to see if she has antibodies against the measles virus and how much. So that concludes this part of the presentation. And again, if you need any help, email or text your instructor. I would encourage you to visit these websites for additional explanation and help on laboratory math.